Okay, good morning, everybody. We have an action-packed day for you today. Let's start right off where we left off on Monday, which is this interesting synthesis of fudoxosin, which I talked to you about as employing the so-called 5+1 approach to make pyrimidines that we'll see in just a moment, wherein in this case, you get an amine that's going to add into that isocyanate and subsequently a cyclization, and that's how you generate your pyrimidinone heterocycle. So where we left off yesterday, I believe Alex gave us a great synthesis of this fragment, but we really were missing a good synthesis of fragment B. So when you look at fragment B there, Sung Han, is there one functional group we can immediately eliminate or simplify? And if Sung Han is not online, how about Nathan? Can you help us?
Oh, sorry, you call me?
Yeah, what's the
Oh,
first?
sorry. So I think isocyanide can.
Yeah, let's address that because we don't want to carry that through a long sequence. We want to make that at the very end. What's a good precursor to an isocyanate?
I guess amino group.
Great. So we know there's a lot of good conditions with phosgene or phosgene equivalents that can get us to the isocyanate in record time. And so now we need a way of putting this together. So we have to think about the two heterocyclic systems that are here, A and B. We don't yet know how to make pyrazines, but we will in a moment. So because we don't know how to make them, it might make sense for us to think of it as nothing more than a simple thiophene. And if we think of this as a thiophene or a benzothiophene, we look at it and we say, oh, well, this looks a lot like a Feiselman disconnection because you can identify very quickly that this position here is your mass cyano group that's hiding. So we know that's a cyano from the many, many times we've mentioned this over the course of this series. And that gets us back right away to a disconnection right across here. And that leads us back to the intermediate pyrazine that you see right here. All right, now we need to figure out a way of making this pyrazine. And the way they did it in literature was starting from the corresponding amino compound, simply because it made the rest of the synthesis rather simple, as you'll see in just a moment. So a Sandmeyer on this compound will give you the chloro compound. And how do we make that? Well, they decided to make this from the corresponding N oxide for reasons that you'll see in just a moment. Now, when we think about disconnecting this compound, we notice again, we've got these highlighted carbon, which we know is a nice signaling element for a cyano. And if we look carefully on the structure for enough time, you'll notice there's a malonyl amino dinitrile that is hiding in here. And so all one needs to do is take that compound and mix it with this. Now the question, this is known as the Taylor pyrazine synthesis. So the question you may be wondering is, what's with that N oxide? And why is it that they chose to take the oxime instead of just taking the corresponding alpha keto system? Why do you think that might be, Nathan? Or perhaps Brendan?
Does it help with the?
Helps with something, yes.
Yeah, it should help with the nucleophilicity.
Well, you basically you have the right idea. It helps with the regiochemical outcome.
Yeah, it helps. Yeah, sort of guide the reactivity in a way where the reactivity is more selective with the oxime there.
Yeah, exactly. In the case of the oxime, that nucleophile has to attack there. There's no choice, and subsequently you cyclize. So that's why you've got the wacky N oxide there, and it may seem like, oh, that doesn't make any sense. But retrospectively, if you need to control regiochemistry and you need the phenyl in a para position relative to the chloro that results from a Sandmeyer, then you know that's the regiochemistry that's going to be the result that works best for you. So that's the Taylor pyrazine synthesis, used pretty often. Today we're going to be covering some of the most exciting heterocycles that are out there. So only second maybe to pyridine, these are some of the most important heterocycles that you see in modern drug discovery. Hard to imagine being a medicinal chemist without having a complete mastery of all of these heterocyclic ring systems. So this 2021 edition of Heterocycles is enhanced over 2019. We've removed some content that is more kind of academic and replaced it with things that are very, very relevant and to the pharma industry, and a lot of consulting corners and things that don't necessarily have direct literature precedent, but they make sense to propose. And they are based upon the principles that we'll learn for each of these heterocyclic classes. So for pyrazines, the easiest way to think about these is often by employing a 3+3 approach. And that, of course, the only issue with the 3+3 approach is you have to think about regiochemical outcome. There's the 4+2 approach, which sort of has a dielectrophile with the dinucleophile. These 3+3 and 4+2 approaches hinge upon the use of an oxidant. Pyrazines love to form. So if you use ethylene diamine and you have any kind of oxidant, air is enough. Sometimes people will use things like CAN or DDQ, but that's really overkill. Just air is usually enough, and that will spontaneously aromatize. These want to form. They like being pyrazines rather than the dihydropyrazines. So some, I think, interesting natural product chemistry that we used to cover in heterocycles, but used to take a long time, and it's probably better relegated to you just going back and looking at the video. Some very cool approaches from Heathcock, Fuchs, who was that? There's a German group that did it as well, and made some, really cool contributions to this, as well as a recent beautiful synthesis from the Riesman group. I would suggest you all look that up. It's a very elegant example of how you can make these unsymmetrical pyrazines. But we're going to focus today more on the ones that you're going to actually see in big pharma. So if you're interested in those academic oriented natural product approaches, check out the 2019 lecture edition. Now, another useful way of accessing pyrazines is through the dehydration of diketopyrazines. This is a very useful way of making systems that look like this. And as you can imagine, the R group diversity is broad because the way you make diketopyrazines is quite modular. Has anyone here in the class made a diketopyrazine before? No one's made a diketopyrazine. Can you anticipate what a good building block would be, Tawe, for a diketopyrazine? And how about Ellie?
Maybe you could start with some sort of amide.
Well, if we start with an amide, that certainly is correct. So there's our amide that you wanted to make, Ellie. Where does this thing come from? Can we just make another amide? And that's the way people do it. They just take amino acids, couple them together, and then dehydrative closure, and you make your diketopyrazine. There's tons and tons of natural products and tons of drug leads that have been made on the diketopyrazine scaffold, and they're all derived from amino acids that are easily coupled and cyclodehydrated to give you the product, which can then, of course, be treated with PLCL3, and now you have a magic library that's made very quickly. The only issue is if you're going to do SNARs on these and the Rs are differentiated, there will be regiochemical problems with that. But if it's symmetrical, obviously the mono and bis substitution is rather straightforward.
Paco, in the 3+3 approach to
yes.
to pyrazines, what would be the typical conditions once again?
It would just be mixing them together with like acetic acid and heat. And you would get, that would.
But would you have to pre-make the amino ketone to prevent it from condensing, or
Yeah,
Would that come from?
often people will make those amino ketones by unveiling them immediately before their use. So they'll either deprotect them or, yeah, usually deprotection and then immediate condensation.
I see. Okay. Okay. Thanks.
This is the 3+3 approach is perhaps best viewed through the lens of the benzo fused system. So if you have this type of system plus that is a manifestation you will see a lot. Okay, so these approaches that I show at the top, the benzo analogs are also known, equivalencies of those. Okay, so
and do you do you still have to have those substituents there for the condensation to proceed?
what do you mean? What substitution?
Do you have to have, for example, the alpha methyl on the ketone? Or
No.
So it's fine
general.
with any alcohol group, it would work.
It's pretty general.
Okay.
Yeah.
Thanks.
All right, great. So varenicline, we've talked about the genesis of how varenicline was addressed through the synthesis of cytosine. So make sure to go back to your notes on the pyridine synthesis. That's maybe lecture number 5. And I promised we would cover how they make varenicline. In practice, they make this on process scale by simply starting with the diamino compound and cooking that up with glyoxal. It's a beautiful story associated with that. Some very interesting benzyne chemistry involved on process scale. Book chapters have been written about it. And as I mentioned last time, it is a billion-dollar drug. But that is the final step to put in the pyrazine ring system. Let's shift gears now to some real-world problems from the archive, dating back many years now. Here's a problem on making a fused pyridine pyrazine, or rather, these two are simply linked. And looking at the structure, one can imagine that one of the obvious bonds to break here would simply be right across here. That's probably the bond that would be most intuitive to break at the beginning. And if we wanted to recapitulate this, probably there's a few ways of doing it. One way is to think about the sort of CH activation approach. The CH activation approach would hinge upon taking a pyrazine such as that, plus your pyridyl bromide, and using some sort of palladium conditions to do, I think of it as a direct HEC, but these days direct HEC is now a CH activation, however you want to think about it. So pyrazine CH activation is known, and then you can imagine to get this chiral methyl group in medchem, the most obvious thing to do would just be an Elman auxiliary and then reduction with borohydride. You can imagine that you could also do the cross-coupling in a more canonical fashion by first making your chiral amine. That could maybe be an Elman auxiliary. And then you could do a directed metallation right there, and then maybe put a zinc species or a magnesium species through no shell, and then do a simple Kumada or Nagishi with the arrow bromide. There's another way of looking at this. Can anyone think of a way of doing this that doesn't involve necessarily a pre-made pyrazine?
Can you do your DKP approach earlier?
Well, the DKP approach is a clever idea, and that would entail the formation of something like this. And now I have to find a way to, once I cyclodehydrate, I'm going to have the 2 chlorines here, and I've got to find a way to differentiate those. So the DKP approach is something that I probably wouldn't necessarily want to do, because that substitution pattern is just not right. For the DKP, I really want the 1,4 substitution of the 2 substituents. What I'm thinking of really is just, this little map here, you may say, Phil, this map is so simple. How is that going to help me? Well, because everything here has a conceptual equivalent. So a conceptual equivalent of this, in principle, this type of disconnection could simply be an alkyne. If I take that compound and I mix it with ethylene diamine, I'm going to get a very facile addition, Michael addition. We know that because that is kind of like a propionate. So this, in my mind, is equivalent to this. Remember? Same thing, reactivity-wise. So if I add in ethylene diamine, it's conceivable through a sequence of additions and cyclizations, then I might actually get out the desired product. And then where does this come from? Well, this just comes from, again, ARBR plus this, which turns out to be commercial, and a Sangashira. So 3 very different routes that you can propose to the practitioner to make a compound like that. How about this? Yep.
So back to Tim's DKP idea.
Yeah.
Did you have the oxygen or the carbonyls at the 1 and 4 location, and then somehow you get the, like with alanine as and glycine as the condensation partners?
You mean a species like that?
Yeah, and then do the POCl3, and then somehow, I guess it'd be difficult to differentiate.
That's the problem. So once I get that dichloro, it's kind of game over. I mean, it's okay to propose perhaps a route where you do a mono reduction of the chloro, but do you want to propose that in a consulting session?
No.
Right. So it's, you know, the fun thing that we've introduced in 2021 with these consulting corners is that they don't have an answer I can point to you. Like I can't point to the literature and say, this is the way they did it. These are speculative. So with that speculation, I'm trying to teach you the suggestions, at least the ones you would start off with. Like, how do you go to SciFinder in a smart way? What intermediates do you start looking for? If you have to make a suggestion to someone that you have a good belief it's going to work, how do you formulate such a suggestion that has as little ambiguity as possible? So it's not that what you said is wrong. And if you put that on a test and you said, oh, I'm going to find a way to dechlorinate the one side and then do Suzuki on the other, or, you know, it's not that it's wrong. It's just not ideal. Okay.
Thanks.
Yep, sure. Let's take a look at this next one. This next one is tricky because we've got this bromine atom here. So that's going to really prevent us from thinking about any kind of cross-coupling we're going to be doing there. So we really have to think about how we might put this together. And it kind of goes back to, again, the simple map we have above. The simple map above teaches you the way you would make this pyrazine. And so thinking about this pyrazine, all we have to do is go back to a compound like this. Everyone can agree that if we reduce that nitro, which is easy to do with iron filings or tin chloride in the presence of a bromo, we will get a nice and efficient cyclization, and that can come from this compound plus that one, which we will show you how to get that thing an antimercury pure in just a moment. Where does this thing come from? That's when you head to SciFinder, and sure enough, you'll find that that is actually a commercial compound, and it can be derived from the bromination if you want to buy an even cheaper compound from the bromination of that. So we're good on this. We added ammonia. We get out our amino nitro compound, which then subsequently alkylates this compound. Where does this thing come from? Well, this thing comes from a very useful reaction that we will employ in this class and hopefully in your future life quite a bit. A useful reaction called the Nugent homologation. And this involves treatment with Corey's illet. So you take that ester, you treat it with Corey illet, and that gives you very cleanly the formation of this without any erosion of your stereochemistry. And then this intermediate can be treated with one equivalent of HCl, again, without touching your Bach group, and that gives you your desired product. So the Nugent homologation is a very useful method to commit to memory because it converts those esters into useful building blocks to make a variety of different heterocycles. We'll see this a few times in the class. Question from the outside?
We have an explosion of questions about the diamine and the alkyne.
Yes.
How that works exactly.
Explosion of questions. So, well, it's speculative, and here's the thought that in the presence of an oxidant, perhaps we would add something like I2, would be probably your best oxidant, and that is going to cleanly deliver that, which should ferociously close, and then you get dehydrogenation. So remember, the saturated systems love to form, and sorry, this should be that with I2. They love to form. So once you get the dihydropyrazine, that it will then dehydrogenate with reckless abandon. Great question. All right, so Nugent homologation, please remember it. And let's move on to the next slide. So quinoxylines, what happens when you take a pyrazine and simply append a aromatic to it? We just saw how one could do this a second ago, but here's another miscellaneous reaction that bears repeating, or at least explaining, because you do see it quite often, and it can be useful in certain contexts. It's named the Beirut reaction because it was actually discovered in Beirut. And mechanistically, I guess we can get somebody to help us out with this one. So benzofurazane oxide, BFO, is an interesting little molecule that is basically the equivalent of just a bis ortho nitroso compound. So the bis ortho nitroso compound resides in the form you see here, BFO, but in terms of its reactivity, it's best used in for mechanistic purposes by drawing out the bis nitroso form. So when we take an enamine and we submit it to this bis nitroso, what do you think might happen here, Alex?
So you'll push down the nitrogen in your substrate, and then the olefin will push into one of the nitrogens of BFO.
Now what?
I guess if you draw the tautomer again of your imine to the enamine, and then you can kind of have the same thing.
And then this attacks again. or this attacks.
Oh, okay. Yeah, that nitrogen could push down.
Yeah. The other problem is enamines generally don't like to go into substitution this way. So probably the equilibrium for this is going to be kind of slow, and it will probably mostly reside on that one. So we need to do something else. And that something else is probably this nitrogen kicking in here, that going there. And you can imagine then subsequent closure. So how would that work? Well, I mean, I guess the best way to
Oh,
do
well, if you add into the enamine, right?
yeah, so we can add in carbon, and that's going to give us a species that looks like this. Which after loss of
Loss of
chloride,
enamine.
gives you your product. So it's probably just the nitrogen is adding in directly here to give you your product. So that's probably what makes the most sense, and then loss of pyrrolidine. And the same thing can work for 1,3-dicarbonyl. So it doesn't need to be an enamine, but rather malonate type species can do the exact same thing. And the resulting product you see from there is what you would get by pushing the same sequence of arrows. So if you're curious, that the Beirut reaction appears to rear its head in strange circumstances. So if you don't take this class or care to do SciFinder, you can rediscover the Beirut reaction with a robot. And that's pretty much what this paper is about. So I'll let you read the mechanism of that and come to your own conclusion on how that is completely known reactivity. Okay, let's move on to the next topic, which is this interesting molecule, which we have now 3 different rings. We've got a pyridine, we've got a quinoxylin, and we have a pyrrole. And so we need a sneaky, quick way of making this. So Noor, maybe you can give us some insight on what ring you might think is the best one to think about disconnecting. Is there a quick way to put this together?
I guess I was thinking that you could break the amide bond and start with the aminopyridine and the pyrrole carboxylate.
So if one makes this, it should spontaneously cyclize. Is that what you're saying?
I wouldn't say spontaneously, because you're gonna have to use some heat because you're putting them in planarity.
Okay. Well, it should close pretty easily. How do we make that?
Well, the first thing I would think of is SNAR.
Great. So we need to convert that amino to something else that can accept a nucleophile, don't we?
Yeah, I guess I would either have it as a nitro or a Bach protected amine, because the position should
The
be.
nitro is the right one. I guess a Bach protected amine would be potentially okay. The only issue is that this is not a great nucleophile at all. You could also imagine, Noor, instead of using that as your nucleophile, you could just use pyrrole. So the same thing would go for this adduct. If we take this adduct and we just treat this thing with carbonyl diimidazole or phosgene equivalent, it will give you the same exact product. That makes sense, Noor?
Yeah.
Great. All right, let's move on to pyrimidines. We've got to move at a breakneck pace because we've got a lot to cover today. So pyrimidines, what happens with, instead of a 1,4 relationship between the nitrogens, we now have a 1,3. These are some of the most widespread heterocycles you're going to find. They're found everywhere, building blocks of life. And We'll talk all about that when we discuss purines in a later lecture, but for now, let's talk about the three approaches which you'll see most often. The most often, bar none, full stop way of making pyrimidines and pyrimidinones and all sorts of pyrimidine derivatives is Traube. This is the way that you're going to use as the go-to first disconnection when you see a pyrimidine or an analog thereof. You're going to think about the 3+3 or Traube-like approach. The next thing you'll consider is possibly a Biginelli. And the Biginelli is a fun reaction because you've already learned it. This is the ASA version of the Hensch reaction to make pyridines. Remember? It's the same chemistry. We've got carbonyl, aldehyde, and instead of another carbonyl, which would be the Hensch to make a pyridine, we use now guanidine or an amidine or urea or a thiourea now to make the pyrimidinone product. And then there's finally the 5+1 approach, which you do see. And the 5+1 approach, either involves the isocyanate here or here. If it's here, you need a leaving group, and that delivers the desired product. So the 5+1 is basically taking all your components and just adding in the amine, and then cyclization occurs, as we saw with fudoxosine. There are some miscellaneous ways of making pyrimidines that come in handy on occasion. And there are basically strange condensations and cycloadditions. Let's talk about the cycloaddition path. The cycloaddition path is rationalizable based on what we saw in a previous lecture to make pyridines. And so if we look at this, we say, oh, I see a diene hiding with these, and there's a dienophile hiding here. And so the disconnection for this as a consequence must be simply taking a triazine plus some sort of amidine. Either of those will work well for you to get your pyrimidine product after cycloaddition. It's rarely used, however, because you need a specific substitution pattern. But when you have that right substitution pattern, this is like a bullet train to give you the product. It's super useful. You can't find a faster way to get there. You can also do this through condensation. So this only happens in certain circumstances when you have rather simple compounds, but when you do, it can be quite useful. And so for problem of the day number 1, we'll take a volunteer to help us off with what happens when you just take cyclohexanone, a couple equivalents of acetonitrile, and triflic anhydride. And if we don't have volunteers in the next 2 seconds, I'll pick on someone.
I can volunteer.
All right, what do you say, Kelly?
So the triflic anhydride will make the vinyl triflate first.
So why don't we just activate?
Okay. And then you can have acetonitrile add into your carbonyl carbon.
Now what do I do?
Then you can have your second equivalent of acetonitrile add into the first acetonitrile carbon.
Okay, now what do I do?
And then if you get elimination of your triflic acid, that gives you your enamine, and that can attack and cyclize.
Brilliant. Thanks, Kelly. All right. And continuing on this theme, this is another reaction. Oh, this is a fun reaction. This was a small side project from Ryan Chenvey back when he was a grad student. He hasn't aged at all. It's funny. He still has all his hair, 4 kids, and still looks totally young. It's incredible. So how did he do this? So he took cyclohexanone, formed amidine acetate, and heat it up and got out the product. So how might we rationalize the formation of this? And So someone can volunteer, or I can call on someone. It is very conceptually similar to what Kelly just taught us. So I'll help you out by drawing the 6-member ring. Who wants to finish it? How about Simona?
Sure. So I guess your formamidine can condense onto your cyclohexanone.
Okay, now what?
And then you can form the enamine. And then that can attack another equivalent of your formamidine. And from there, I guess you can just cyclize and lose ammonia.
Fantastic. Great. All right, so with that, let's move on to some case studies for actual uses of all of these ways of making pyrimidines. I should note that what I show on the screen here summarizes roughly 10 or 20,000 papers. So there's a lot here, but we've tried to distill it as much as we can in a very small introduction. But if you commit this to memory and really understand it, these tiny little rules will be enough for you to do very smart sci-fi enduring in the real world and make suggestions off the cuff that make a lot of sense. So let's move on then to the case studies. So we've got this one, LY231514, and I'm just gonna make it really simple because I don't wanna think about that arrow group. So let's just draw this so we don't have any confusion about what we wanna analyze. And I'll just put AR here and make it all nice and simple. And so now we have to think about making this compound, and we've got two different rings. We've got A and B, and so there's obviously going to be two different directions we can go on, just like we did with all of our fused heterocycles of the past. Any sort of inclination, anybody have an instinct as to which way they'd like to go? Do we build off of A, or do we build off of B? There's really no wrong answer here. We're going to do them both.
Building off A seems pretty reasonable if you leave behind like an amine.
And then for our other component, you can imagine maybe just using a standard Bischler type reaction. Something like that, right? And hey, Alex, I've got two amines here. How come is there gonna be any problem with that? I need this one to be adding in to that electrophile.
It should be selective for that one.
Wow. Why?
It's more like an aniline nitrogen than the other one would be.
Great, brilliant. Yes, this one is pretty much, like an amide, very, not very nucleophilic, not very basic. Whereas this one, boy, yeah, just like you said, it's like an aniline, and so it should condense no problem. Does the other method make sense if we break the other ring? Let's take a look at what it would entail. It would mean we would use the essentially 3+3 approach. But now we need to make this tri-substituted pyrrole. Do you want to do that? Does anybody want to do that? This one is harder than this one, in my opinion. That's how you know you made which disconnection to go for. You just do both. There's no wrong answer, right? During an interview, you propose both, and then you look and you don't even have to let them know which one. You say, this is what I would do logically. I'd break them both up. And then when you break up the wrong one, you say, see, that's the wrong one. And you go the other way. and you get bonus points. You're like, wow, that's very analytical of you. That's great. And you get the job. All right, let's move on to this one from Pfizer. So we need a way of rationalizing which way to go. We've got two rings. And so we can, of course, do both ways. And so if we break, I'm just going to say randomly, let's just build off A from B because I just feel like it. Does anybody like that? I mean, it's not horrific. You could form from here the corresponding dichloro compound after condensation, and then this compound you could imagine comes from, because we've got the hiding nitrile there. You could imagine maybe it just comes from that plus. So it's not terrible, right? It's a viable disconnection. And maybe in process scale, that might be the way to go. It's certainly a disconnection you'd want to consider. But what happens when we look at the other disconnection? Well, if we do what Alex just taught us a moment ago, we end up at the Bischler disconnection again. That feels pretty good because we know already from, I think, lecture 1 or 2, early on, we knew how to make these systems in a stepwise, clean fashion from the trichloropyrimidine. So everybody already knows about the haloselectivity of these and the order of SNAR with an amine, wherein addition number 1 takes place here, addition number 2 takes place here, and addition number 3 takes place here. Bischler, and you're done. So that is so good that maybe even the process chemist would want to do that one, as well as the med chemist. An interesting example of where the two retrosyntheses are kind of in harmony with each other, process and med chem. All right, let's take a look at this interesting one from Novartis. This is an OPRD paper. And again, we want to take a look at ring A and ring B. If we think about the sort of disconnection that Alex has been teaching us, then we would go back to an intermediate like this. Alex, any problems with that disconnection for this one? What would be a potential issue you might warn your colleagues of before they do this? Any thoughts? Well, I personally would be worried about this nitrogen versus this nitrogen in the cyclization. So that would worry me a little bit and cause a little bit of trepidation. So let's just take a look at the other approach, especially if this was process scale. I would worry about getting a little bit of that undesired regioisomer. If we think about the process scale route to this compound, then we can imagine, well, that just might come back from this compound.
So would you worry about that, the nitrogen also like becoming a bridgehead?
That is a good point. That is a possibility, although with an electron-rich system like this, it's likely that you would get carbon attack. But yeah, a bridgehead system. When we talk about bridgehead systems, we'll see that kind of thing. But in this particular case, because it is rather electron-rich at that position, the carbon, you probably would get cyclization in the Bischler mode. So we've got the cyano here as a result, and an NH2. There's our hiding cyano, as always, is right there. and our amino group. Now, where does this thing come from? Well, one can imagine this just comes from the same ketone we had before, but we're going to put the amino group in there, which is unveiled, immediately condensed with malonyl dinitrile. So process scale, you get out the desired product. Now, how do we convert that into the final API? Well, that is first treated with AR, amine, plus triethymethyl orthoformate. And that gives you this compound. Now, in a stroke of real brilliance here, the process chemists simply take this compound and heat it up with ethylene glycol and water and ethanol and heat it up. And an interesting rearrangement takes place, a formal rearrangement called Dimroth. We saw this to a small extent in Aaron Sather's guest lecture. But the nice Dimroth rearrangement here takes place by way of a ring opening, bond rotation, and then ring closing to get us the AR and the NHAR in the thermodynamic position. So this goes by way of a thermodynamically driven process through ring opening, ring closing. I want to mention a modern method that might be extremely useful to you and all of the listeners out there that takes advantage of this kind of Dimroth logic. And it is a paper that was published in Orglet back in 2009. And what page is this? 1421. And the key thing to remember in this reaction that I'm going to show you is it kind of uses Dimroth logic. So we learned a while ago that if you have a system like this, and you treat it with something like BOP and DBU, we learned that you're going to get O activation by this kind of phosphoramidite intermediate. And then when you subject that to a nucleophile, let's say we add an amine, the product is what you would expect, where you've got that. Now, if we are well versed in Dimroth and think about another way to do this, these folks at BMS, led by the great Percy Carter, found that you could use Pay2, and that, instead of leading to O activation, led to N activation. And because it is a uranium salt, the intermediate you get is quite a bit different. And it looks like this. Now that uranium intermediate can open up to give you this intermediate. And upon reclosure, guess what the product is? Indeed, the NAR. So this is extremely useful chemistry when you're trying to do N arylation of a system like that, and nothing is working, your Chan lambs are not working, your Buckwalds are not working, your Ullmanns are not working. And then if you try a Chan lamb or a Buckwald or whatever, maybe you might get, you know, the wrong type of retroselectivity. Maybe oxygen is attacking in the aryl bromide you're using. Whereas this approach goes by way of a Dimroth type opening closure to give you the desired product simply by changing your peptide coupling agent, just switching over to this Carpino reagent, He2. The uranium intermediate is formed, which prefers N activation over oxygen activation. This transport inhibitor can be made very quickly. It's an interesting paper in OPRD that has no less than 28 authors. So I thought we would pay it a little bit of homage to simply go through the quick disconnection of where you would make this from. And it comes by recognizing that this is nothing more than an SNAR. And so the building block to make this is simply from that. So SNAR followed by dechlorination, and you get your product. Where does this thing come from? Well, if you're stranded on a desert island just with coconuts and no aldrich, perhaps you can find a little bit of POCl3 and some formamidine acetate somewhere, and that would give you rise to these intermediates that you would need to make as MacGyver on that island. And this could be L-methoxy as well. And then PLCl3 would give you the product if it was the L-methoxy version. But of course you can buy this, it's very cheap. All right, great. So let's move on to problem of the day number 3, where I'm basically going to ask you what we've been doing over and over again. So does it make more sense to start with A and then fuse on to that B, or does it make more sense to start with B and fuse on to that A? Who is going to volunteer to earn some Doge coins, pre-Doge, I should say? And if we don't have a volunteer, we might as well just call on someone. So how about Daniel?
So maybe.
No wrong answer.
I was thinking A to B.
Okay, let's see what it looks like. So we're going to do A to B, and that means we're going to need 2 components. We're going to need to have this one. And our coupling component will be something like this, because we remember the quinoline lecture. This is nothing more than a hiding quinoline. Daniel, did you see the quinoline when we first put this problem up?
Yeah.
Yeah, this is just a quinoline. If you pretend that this is a benzene ring, it's quinoline. And then couple those 2 together, you got symmetry. Alex taught us why this nitrogen is more nucleophilic than the other one. So we are good to go on that. Now, is the B to A disconnection really that bad? Let's take a look. Maybe it's not so bad. What do you think, Daniel? Do you like that compound?
It looks a little complicated.
Yeah. This is harder to make than this. How do you like that? Retrosynthesis is supposed to make things easier, not harder. Don't forget that. So unless you have a snazzy way of making that really quickly, this is a way of starting from junk. This is nearly free. This is made from just an alkylation here. So you can make analogs all day with your favorite benzyl halide. Alkylate the beta keto ester, dump and stir with the triamino pyrimidine, and that's it. You start printing money. Okay, let's take a look at these 2 problems from the real world. So this one, we've got, again, the system of A versus B. And there is no literature prep for this compound. There is no hidden SciFinder, so we just have to use what we think might be good and speculative, but the most logical thing we can think of. So maybe Carter, you have a way you want to start off, and then I'll take us back from there. Which one do you prefer instinctually? No wrong answer.
Instinctively, I was thinking A to B.
Okay, so A to B. would mean that we are going to start from an intermediate that looks like this. That would probably instantaneously cyclize to give you a product. Would you agree?
Mm-hmm.
Okay, and now I need a way of making that. And my favorite way of activating anthranilic acids is through intermediates that you should know the name of. Does anybody know the name of this intermediate? These are isotoic anhydrides. So if you take the isotoic anhydride and add vinyl magnesium bromide to that, you'll get out the product. Where does this thing come from? All of this is proposed to be done in one pot, for which there's good literature precedent for this type of thing. And that just comes from that, which is a known compound. You go back to SciFinder with this one, you'll find it's known. And but if you don't know that it's known, you can still derive a synthesis of this from the corresponding dichloro compound. Which makes its way back from a compound which is even cheaper. This compound is nearly free. In fact, rumor on the street is that the bottle that contains it is more expensive than the actual compound inside. But if you can't even afford to make that, you can imagine it comes back from sort of even cheaper components, maleic anhydride plus urea, followed by oxidation. All right, great. Carter, that was super. Well, is the other disconnection bad? Well, what would it be? It would be 3 plus 3. 3 plus 3 is the other disconnection. So let's just draw it. It would require we make something like this. Do you not like that, Carter? It's not terrible, right?
It's not terrible.
Not terrible. And we can imagine maybe if we look in the literature, we'll find, oh yes, this thing is commercially available. And we can imagine maybe a directed lithiation to that position, quench with NCS, reduce the ester to the aldehyde, and then dump in your favorite nucleophile, something like this. Or you could dump in urea and then PLCl3, whatever. And the 3 plus 3 approach would serve you well. So this is a case where really I would give both routes to the practitioner and let them decide based upon what building blocks they have in-house, because they're both they're okay. All right, let's take a look at this next one, a strange little propellane, which appears to be sort of all the rage these days. How do we put that together in a very quick way? Now, when I saw this problem, the first thing I thought about, of course, was 3 plus 3. The problem is, if we're going to start with a 3 plus 3 approach to make this compound, I need access to something like that. And that can sometimes be problematic to get your hands on, not so stable. So that's one possibility you can mention to the people, and maybe they'll be okay with making a compound like that. But more likely, there's a direct way, and that direct way would use some really cool Boger cycloaddition chemistry via this intermediate. This is a recent Jack's paper. Really cool. That cycloaddition takes place via the intermediacy of this, kind of along the lines of what we've learned already when we see cycloaddition chemistry to make heterocycles. Which after cycloreversion, lose nitrogen and lose ammonia, you'll get out your desired product. So 2 routes to get to the same thing, and the propellane nitrile is your precursor, which is easy to make. Just take your propellane nitrile, dump in ammonia, and that gives you your amidine, which is now ready for the show. Either the 3 plus 3 approach or the cycloaddition. Either one is good. All right, let's move on now to variolin. In variolin synthesis, we have to try to identify some hidden symmetry. Can anyone see the hidden symmetry?
If you disconnect alpha to the pyridine nitrogen.
Brilliant. That is brilliant. Now look what happens. Awesome. How do we make that? Just from the corresponding ester. We do some sort of no-shell magnesiation, add it in twice, and then cook that sucker up, and it will cyclize, and you'll get out variolin. That's probably the best way to make it. There is a stepwise way of making it as well that thinks about this in terms of stepwise disconnections getting all the way back from an aza-indole. So I'm not going to go through it because of lack of time, but I will refer you to the 2019 lecture. In that lecture, you'll find an approach which starts off from an aza-indole. That aza-indole can be made via a Hemmetsberger type reaction. After that, we get an annulation take place here, and then a Vilsmeier reaction to forge that bond, followed by a 3+3 approach to put that in. So that's your 10-second analysis of the stepwise route to make this, but I really like Carter's instantaneous recognition of the symmetry, which can also be used to put variolin together in very short order. Great, so let's move on now to the final class before we get to triazines. Now, pyridines are really great heterocycles. You see these a lot, tons of FDA-approved drugs, tons of compounds in the clinic with pyridines in them. So it's really important that we kind of master these. And the ways of looking at this are, not surprisingly, going back to this kind of 4+2 condensation approach. You take a hydrazine and you find yourself the same precursor we've been using to make pyrols and purans and thiophenes. That 1,4-dicarbonyl will come into play yet again. So remember, go back to lecture 4 when we talked about all the equivalents of 1,4-dicarbonyls. We'll use them here again, but instead of adding ammonia or instead of dehydrating or adding sulfur, we're going to add hydrazine and we'll get out a pyridazine. You can also imagine the cycloaddition approach from a tetrazine. Usually these tetrazines have R groups associated with them here to stabilize them. You'll recognize this has become rather in vogue now with the advent of click and related bioorthogonal chemistries, because those reactions are extremely quick. So those tetrazine so-called ligations that now exist are based upon this type of analysis to make pyridazine adducts. And then you can also imagine, strongly depending on your R groups here, that you can imagine a condensation taking place reminiscent of Gewalt for thiophenes, but now we've got the dicarbonyl condensing, and then after that, a hydrazine addition. Finally, one that is really good to remember is when you're making these synilins, the von Richter cyclization, wherein you can treat these compounds with sodium nitrate, you diazotize, and then those will collapse and cyclize on to make these types of synilin-like products. But you see this a lot, this type of chemistry. Always remember that when you see the NN bond, you can access it either from hydrazine, but in the case of the aromatic systems, you can also get them from the aniline. Don't forget that. So the aniline can be converted to the hydrazine just by a diazotization. So remember that. Okay, let's take a look at a pyridazanone. These are found all over the agrochemical literature. Tons of patents on making these types of compounds. Super useful. And the way you would put this together. So perhaps Jun Chen can give us a thought on what type of intermediate might rapidly give us a pyridazanone.
Yeah, the ester and with hydrazine.
So that's great. What you're going to be thinking about is something like, right? Is that what that would, if you could make this, something like that would give you, when you treat it with phenylhydrazine, would give you the product, right?
Yeah, but it's maybe too complicated. So
well, we need a functional equivalent of that. And so the first thing you can do is get rid of the methoxy. Let's turn it into this compound, because we know those two bromine atoms are not equal. One of them is activated and one of them is not. This guy is ready to go. This one is going to stay put. simply because this one is kind of like a beta to a electron withdrawing group. So now the secret little trick that people use to make pyridazinones in a very cheap fashion is taking an equivalent to Junchen's intermediate, basically just a cyclized form of it. This compound is known as mucobromic acid. It's extremely inexpensive, and it, in the presence of hydrazine, will give you that product because it is basically the operational equivalent of Junchen's intermediate. All right, so let's do this in real time and learn how we can use these various techniques in some real world problems. So for this first session of Consulting Corner on pyridazines, we've got 3 different heterocycles again. Look at this. We've got a pyridazine, we just learned about those. We've got an we've got a quinolone right here, and we've got a pyrazine there. Wow, that's a great one. When I see problems like this, I just get giddy with excitement. This is super. How are we going to disconnect this one? Is there any hidden symmetry we can take advantage of? Are there any disconnections that look like they're sort of waiting to go? Are there any things you look at when you see this molecule that make you say, I want to disconnect there first? Tim, what's your knee-jerk response? Or Sunghan, who is speaking? I'm sorry.
I'm sorry, I'm just thinking about cut the amide bond.
Cut the amide bond. You mean here?
Yeah.
Okay, and that will require another bond to break as well. Which other bond goes with it?
The sp2 carbon-carbon bond.
Yeah, that's pretty good. That leads us down basically a road that simplifies things immediately. Look what Sunghan has just done for us. That's it, right?
Yep.
Yep. How do we make this creature? You've gotten rid of the quinolone for us. Now we need to think about, we've got a pyrazine linked to a pyridazine. It's almost symmetrical, isn't it? It's almost perfect. How do we make it? How do we get the symmetry out of this thing? We got to tease it out. How do we get it out? Just put NH there. NH is fine. So what could we do to desymmetrize this molecule? Anyone? Well, there's an obvious carbon-carbon bond we have to break, isn't there?
Vilsmeier.
That sounds great. Vilsmeier. Potentially, either on the diamino compound or by the Bach compound, lithiation, we should be able to put in that aldehyde. So either through Friedel-Crafts or through lithiation and quenching, we should be able to get that. Now we just have to find a way to make this. And there's a few different ways of thinking about this. When you go to the literature, you're going to find that this compound is extremely inexpensive. And then luckily, if you start searching random heterocycles papers for additions, SNARs on a compound like this, you find that diamines and amines have 2 opportunities for addition. They can either add to give you that product, or they can add to give you the product you want, that one. And it turns out that you get the major product is this one. So you can imagine taking that compound, dechlorinating it. You can imagine adding 1 equivalent of cyanide to there, then dechlorinating, and then dibol to give you the aldehyde. A lot of options from this very, very inexpensive material. There's another possibility, which is let's just do tetrazine chemistry. You can imagine if you take this compound and you add it into this, for which there's a really easy prep to make, you would also get the product. So these are all reasonable suggestions to start with. How about this next one? We've got a pyridazine here, and we have it linked to a pyridine. And you might want to look at this bond and you say, hey, Phil, I'm obsessed with this bond. I really want to break that bond. I know you do. I know. Everybody wants to break that bond, but it's not going to work the way you want. The problem is when you try to break that bond, you end up with two coupling components, which are probably not going to be great. Like, you see these kinds of problems a lot. We talked about it before, where they block you from doing the rock type chemistry. Here, they're blocking you from doing cross-coupling chemistry because I don't know what to put here. And similarly, I'm not sure what to put here. You can tell people all day about maybe cross-electrophile couplings or other types of bizarre things, but I don't know how you differentiate that halogen, that halogen, that halogen. I can't give you a disconnection there that makes anyone sort of happy to run to the hood and not expect a bunch of messy tarry mixtures. So I need to decide, how am I going to do this? How am I going to do it in such a way that I don't need to use cross-coupling that's going to be so challenging, and maybe make the pyridazine from scratch. So if you look at this compound, you say, well, why don't we think about what Junchen told us before? Junchen taught us that we're just looking for the dicarbonyl. We're going to look for that 1,4-carbonyl. So that would get us back to something like this. That's our 1,4-carbonyl hiding. And you may say, hey, Phil, that's a really strange depiction of a 1,4-dicarbonyl. Why did you do that? Well, the reason I did it is because this is nothing more than a furan. It's hiding. So this cloaked furan upon treatment with a little bit of an oxidant, you can use bromine, methanol, sodium carbonate. That's the sort of standard conditions. Will now give you that, which when treated with hydrazine, will give you the desired product. Now, how do we make this compound? Well, it turns out that this one is rather straightforward. Now we can start with something where we know we have differentiation. So we know we can differentiate these really easily. That one's going to do our palladium coupling first. And we know that this boronic acid is going to be a stable one, not a messy one like the pyridazine one would have been. And this just comes back from a deprotonation of that position. And you'll find yourself very easily able to get that furan from commercial suppliers. Great. So we have 17 or 18 minutes now to talk about triazines. So we've got a few different varieties of triazines. We've got 1,2,4, we've got 1,3,5, and we have 1,2,3. We'll talk about all of them. The one that is probably the most challenging and thought-provoking in terms of optionalities of disconnection are the 1,2,4s. So the 1,2,4s can be disconnected from a dicarbonyl and an amidrazone. Where do we get the amidrazones from? Well, we learned this, I think, already, but they're from the nitriles adding in hydrazine. So the amidrazone is a great precursor. The other way of doing this is thinking about 1,4-dicarbonyl logic again, but just putting an amine there. And that gives you these alpha amido ketones plus hydrazine. And then finally, ring expansion. The mechanism of this ring expansion we'll cover in problem of the day number 4. Hopefully someone's ready for us for that. So those are the three kind of thought processes when you're thinking about making these 1,2,4 triazines, which you do encounter quite often. And they can be some of your most vexing consulting problems. The 1,3,5 are simple because almost everybody does that. And so 1,3,5, you really don't have to belabor. 90+% of the way people are making these 1,3,5 triazines is by a sequential addition. So from no reason to really go and belabor that point. So let's take a look at the 1,2,3. How do people do this? This is problem of the day number 4. Any volunteers before I call on someone?
I guess you will form a nitrine in this oxidation condition.
That was easy. Don't even need to draw anything here. Brilliant, Sunghan. So yeah, you make a nitrine 1,2 shift, and that's how you make your triazine, 1,2,3 triazine. Great. Certainly not going to use an azide to make that. So yeah, that's one of the best ways of making those. And then tetrazine, which of course, as I mentioned before, are sort of more popular than they used to be. And those are usually made through, often through condensations of nitriles and hydrazines via the intermediacy of the dihydrotetrazine. There's an interesting example of this in the medicinal literature, that is Temodar, and we cover that in the 2019 lecture, but for lack of time, we're simply going to go forward on this consulting corner, which luckily we have now a great amount of time. Been very good with the time management today. So let's move on to the last consulting corner, which gives us a real exposure to triazines. Unlike the 2019 lecture, which I felt was too abstract and not sufficient to prepare you for the real world, here's some real world stuff. So these are the kinds of triazines and the use of triazines that you may encounter in your life. Let's take a look at this first one. How would we go about making that? I'll give you a few seconds to think about it, and then perhaps someone can give us a general thought on what they might do. We'll take a look at this one first. No takers? Any general thoughts on this compound? What atom might we put in at the end, let's say?
Bromine.
Okay, let's start off with that. That's all I needed.
Can you trace it back to a symmetrical dicarboxylic acid? Oh, I think
nothing is going to be symmetrical.
Yeah, sorry.
Because it's the 1, 2, and then 5. You're kind of stuck on symmetry. That's part of the problem of these triazines, is they kind of screw you up in terms of symmetry. You don't really get it anywhere no matter how you cut it. So we've got to aim for something like this, and we can imagine POBr3 or PBr3. Some conditions like that might be able to sell that bromine, or if the chemist is flexible, they may be willing to do POCl3 as well. So now we have to build up this compound. And the challenge of building up this compound, were we to do it, let's say, through an intermediate, like, let's just draw it in a different tautomeric form. And when we do that, we recognize that this probably could come from something like this. Now, to convert that to the product, on paper, what I would need to do is treat this first with hydrazine, hope and pray that it adds there. Then I need to treat this with ammonium acetate, then some sort of oxidant, and then finally, our POBr3 or POCl3. That gets us to intermediate A, let's say. So, Tim, what's the problem with that approach?
You have regiochemical issues.
Oh, I got big issues. Yeah. Gee, I don't know what to do with that. That's a big problem. So I kind of need a protecting group for the ester, don't I? I need something to shield this. Did we learn a good way to shield those things? I think we did. I think it was back in lecture 4.
How about reduce it?
All right, we can imagine reducing it, and let's say we use, O, R, whatever your favorite protecting group is there. We have that. That's one option for you. Sure. Is there another way that we can do this so we don't require, now keep in mind the other sort of pragmatic issue of these compounds, and ones that you don't get exposed to until you talk to these people who are actually doing the chemistry, is these are miserable water-soluble compounds. If there's any med chemists out there who've made these, they're probably chuckling now because they know how bad these compounds are to deal with. So you probably don't want to take that small molecular weight, water-soluble, annoying compound, deprotect, and then oxidize. I wouldn't want to do it. Now on paper, Junchen, you write that on the exam, 100% credit. Wonderful. But in the real world, what they want to do is just sort of unveil something at the end. Now the orthoester is not going to be that easy to make or handle. So my favorite way of protecting an ester or an acid is just use the furan. This is just a furfural derived starting material. You can buy this acid very, very cheap, and do the exact chemistry I just showed you. And at the very end, you can unveil it with anything will work. MCPPA, KMNO4, we'll just chop it off right away. And if you do it under acidic conditions, you don't have to worry about any N-oxide formation or oxidation of the triazine. All right, so we're good on this first one. How about this second one? What we can think about is, again, getting rid of a few substituents. In this case, we can imagine that maybe this comes from that by way of benzylic oxidation with NBS and peroxide, followed by KCN and then hydrolysis. And the reason we propose this for this case is if you look, you'll find that this actually readily available. Actually, it's commercial and pretty cheap. So we could start with this compound and simply do a Sandmeyer to get the product. Where does this come from? Well, if you wanted to make it, and you didn't want to buy it, you can make it simply by treating this with ammonia and an oxidant. So they let this sit with ammonia for a while, then they add in KMNO4 to oxidize up. The ammonia adds in at that position, and then oxidation gets you to there, or you buy it. But that's a tricky compound. Looks simple, but there's a reason they asked the question. Not known.
So if you wanted to disconnect those triazines by a nucleophilic addition of a malonate, would that displace?
Okay.
Would that displace the bromine that is in the 2 position or the other one?
Yeah, good idea. So you want to do an Ullmann or just a SNAR?
Or just SNAR, yes. If you do SNAR.
It's a good question, Nick. I mean, I wouldn't propose it unless I could go in literature and find. Now I know what the rules are if it was a pyrimidine, but when you add that extra nitrogen in there, I'm not sure which one is going to go here or here. I might use C13 shift analysis. I would check for the availability of that dibromotriazine. It's a good idea. It's certainly something you'd want to search for, but if you didn't find any kind of precedent, probably the practitioner would want something that they knew would work from the beginning.
It's likely to be a mixture, right?
I would predict that if I were to propose this, the chemist in question would say, don't you think you'd get a mixture? Which is why I wouldn't propose it.
And also for the one on the left as well, you don't think the other bromine would be distinguished from the one that's alpha to 2 nitrogens?
It's rough. It's rough, Nick. I don't know. We could look into it. There's not much known about those dibromotriazines. So, best to leave the dihalo antics to the di and mono as a heterocycles, because that's very well understood. When you start getting into the dihalo triazines, everything is screwed up.
Okay.
Partly because there's just not a lot of literature precedent for these compounds that are hard to handle, water soluble. So if they have been made, not a lot has been done with them. But
Okay, great, thanks.
all right, this one doesn't have a triazine at all. So what's with this one? You know, this is a problem that you know there was no good solution to this one. So where's the triazine here? Anybody have a 2-second solution to this one?
Does it come from a cycloaddition?
Oh yeah, wonderful. So what is a cycloaddition partner? Well, it's just this. And this one is actually known in the literature. So just this plus 77% yield product. It's kind of like the bugger cycloaddition that we learned to make pyridines, but with all those chlorines on there, works as well. And the final problem in the last 5 minutes of the class are analogs of this now benzo-fused triazine. So how are we going to, it's an amino triazine. This one is rough. We've got diverse aryl groups, which is a signaling element for let's put a halogen atom in, because they want to do Suzuki's and all sorts of stuff at the end. So why don't we just throw a chlorine in there? All right, now we need a way of making that. Now you might look at, yes, go ahead, Simona.
I feel like I see a guanidine in there. Can you disconnect between guanidine and like a nitroarine?
Okay, let's do that. Let's see where it leads us. Is that what you want to do?
Yeah.
You definitely got the job. That's pretty good right there. Now, if you take that and you condense it together, what do you think the product is going to be? Is it going to be the oxidation state that you want in the product, or is there going to be something else there?
It's probably gonna be, you're probably gonna have to reduce it.
Exactly. That's your initial product.
Yeah.
Which is super easy to reduce that, and you get out the product. Brilliant. Awesome. Let's shower her in pyridose. Yeah. Okay. That was great. And we have 3 minutes, so we might as well think about another way of doing this. Let's imagine that the Simona route, which is known and would work, let's imagine that in certain cases, the practitioner says, hey, Phil, we don't want to have any triazine N-oxides because we're worried about an energetic event. So I've heard those kind of concerns before. So if we can't make the N-oxide because they're worried about explosions, potential high energy properties of that intermediate, is there a method we could use to get around that? Well, we just have to go back up here and look. Let's see, I forgot how to do this, so I'm just going to look back at my, let's see, we did the cyclization. This is essentially what we did on the left-hand side, what Simona did, except one side was a nitro, where, you know, that was connected to there. So we kind of did that already. That one doesn't really apply, but oh, look at this one. Let's see what happens if we do that one. So that might come back from that. Now, the only problem with this is that, of course, it's going to come back from an easy to make 2-amino-benzimidazole, which we haven't learned how to make yet, but guess what? We're going to learn it. Is it Friday we learn it? Yeah, Friday we're going to learn this stuff, folks. So stay tuned on that. Now we just need a way of doing electrophilic amination. And so that's where you go to the literature. We're going to go in SciFinder and say, what's the selectivity of aminating a benzimidazole like that? And we will find that the regional selectivity actually favors, in the case of chlorine, 97-3 in the desired fashion. So that's great. And then we can look further, and it's known that these benzimidazoles that are aminated in the presence of an oxidant like PETA does what Sung Han taught us, which is the nitrine formation 1,2 shift of the carbon to give us the product. So two very different ways of making this. Personally, I would go via the Simona route, but there's also this alternative if they desire it. So that's it, folks. We're just perfectly on time, and the excitement has just begun. Friday, we're going to talk about azoles, and of course, that's an enormous class of medicines that cannot be missed. So have a great Thursday, and we'll see you on Friday.